What happens when 2 nuclear reactors worth of demand disappears before the grid can even blink? On July 22nd, more than 3 gigawatts of data center load dropped away in about 30 seconds, and the impact of that drop was far greater and more important than many of us could even see. So here's the claim I'll stand behind. The grid can carry AI only when the data centers become part of the stability system itself. So come with me, let's get into it. On July 22nd, a single transmission line went down near a data center corridor in Virginia, close to Washington. Protective relays sensed the fault, and banks of AI training clusters and their power systems tripped offline together. So in about 30 seconds, data centers stopped drawing more than 3 gigawatts from the PJM power grid. That's roughly 2 large nuclear reactors worth of demand disappearing almost at once. So the voltage spiked. The disturbance traveled from Virginia towards Chicago, and it took the system about 10 minutes to settle. That sequence reveals a new kind of grid problem. For more than a century now, grid engineers have prepared for power plants to fail. A generator disappears while homes, factories, and offices need to keep drawing electricity. So the grid responds by bringing other sources online in order to balance that loss. Data centers flip that problem around entirely. A large campus may draw more power than a city. When its electrical protection systems sense trouble, thousands of those machines can just disconnect within milliseconds, but the power supply remains, even as the demand just vanishes. So imagine pushing really hard against a door when the person on the other side suddenly just lets go. That force has to go somewhere. On the grid, that sudden mismatch shows up as a voltage or frequency spike or disturbance. Other equipment then has to absorb it before the wobble spreads. Now, traditional industrial loads rarely moved at this scale or speed. A steel mill doesn't just disappear in milliseconds, for example. Millions of homes don't coordinate their appliances and then switch everything off together. But AI campuses can. Though their computers operate in a huge synchronized block, their protective systems can also react as a block, and that makes campuses less like an ordinary customer and more like a giant grid component. Power companies are constantly using predictive measures to determine the right amount of load for a given situation. With the heatwave a few weeks ago, for example, the grid planned for maximum usage and ratcheted every available power source way up to the maximum in order to meet that demand. If something like this would have happened during such a situation like that heatwave, we would have seen far worse than just lights flickering, which is basically what we saw in this incident. There would have been real and possibly sustained outages in the middle of a heatwave. Ricardo de Azevedo, who is CTO for On Energy, said that this incident was a canary in the coal mine. The reason grid operators view it this way is because as data center load increases, if our infrastructure is not also built out and improved in tandem, then these events will get far more frequent and be far worse. So all of that means that the July 22nd event crossed an important threshold. Gigawatt-scale computing is now large enough that how it disconnects can affect an entire electrical system spanning several states. That doesn't mean the grid has reached some fixed limit on intelligence, but it does mean that the engineering rules have fallen behind the load. Now, the correction has already started. The question is whether it's happening fast enough. For example, Texas grid operator ERCOT now requires covered large computational loads to show that they can ride through a disturbance. Now, ride through means staying connected during brief voltage or frequency wobble. The campus absorbs the shock and keeps operating instead of joining a stampede for the exit. Now, that may require batteries or another source of on-site power, and it also requires control systems that can separate the campus from the disturbance without dumping its entire demand onto the grid at once. On Energy is already shipping campus-scale uninterruptible power systems for this very purpose. When the wider grid wobbles, the data center can then draw on its own stored energy and smooth that transition. And that equipment turns the campus into part of the solution, so the data center can protect its computers while helping the shared system remain balanced. And it also places the cost in the right place. Until now, the wider grid could absorb much of the risk that was created by some giant new load. Utilities would harden the system, build more capacity, and spread the bill out among customers. Ride-through equipment and on-site storage place the cost of a campus's electrical behavior on the company building that campus. Now, the same principle appeared in the unanimous House committee vote that we covered just a couple of days ago. That bill would require large data centers to pay for the grid upgrade that their projects create. Federal regulators are moving on reliability, too. Earlier this month, FERC ordered NERC to draft mandatory rules for large computational loads, including AI data centers, after several events in which hundreds of megawatts just disappeared within milliseconds. The new event here raises the scale from hundreds of megawatts to more than 3 gigawatts, and that makes this mandatory standard much harder to postpone. The technical answer is becoming visible. We need to require large campuses to ride through common disturbances, we need to add on-site storage, and we need to design interconnections around the way that computing load actually behaves. The institutional response, though, is far less clean. E&E News obtained emails showing that Virginia regulators downplayed residents' health and reliability concerns about the concentration of data centers. Those residents live beside the substations, the transmission lines, the generators, and the construction sites that serve this build-out. So when the grid fails or local pollution rises, they don't experience it as some abstract infrastructure problem. Their proximity gives them evidence that a company presentation may leave out, sometimes intentionally. Yet those channels for public scrutiny are also narrowing. Ars Technica reports that the Environmental Protection Agency is moving to cut public notice requirements for data center backup generators, and that would give nearby communities less opportunity to weigh in as companies place more combustion equipment around their homes. The federal government may describe that rollback as just a way to accelerate construction, but its practical effect is to remove people from decisions about the air they breathe and the machines built beside them. And there's another proposed answer that's already missing the capacity it promised. Canary Media reports that several data center operators have started wiring gas turbines directly to their campuses. They want to avoid long grid connection queues and create what they present as a reliable source of power. Now, those off-grid gas systems are already falling short of the capacity that operators promised. The campuses still depend on the shared grid. They also bring the cost and the pollution of their private generation into the surrounding community. A company can call its power system off-grid, but if that system can't supply the promised load, then the physical connection tells the actual truth. This is why public scrutiny and firm engineering standards belong together. Residents can identify the local harms. Grid operators can measure the system risk. Binding rules can make the builder pay for the equipment needed to solve both. Now, the July 22nd fault was indeed serious, but it also delivered unusually clear information. The data center of the near future cannot behave like some passive customer that buys electricity and then leaves stability to everyone else. At gigawatt scale, it has to help hold the system together. That means storage, ride-through controls, honest capacity plans, and an interconnection agreement designed for synchronized computing. Every major infrastructure system learns through failure. We have seen this time and again. Bridges, for example, they gained stronger codes after collapsing. Aircraft gain new checklist after an accident. Power systems add protection after a disturbance reveals a pattern that engineers hadn't fully planned for. So this event has now revealed a pattern. A single line went down, and 2 nuclear reactors worth of demand simply vanished. The grid answered with a voltage spike that crossed several states. The next generation of campuses will be built around that lesson. That is how the grid eventually carries far more intelligence than it can carry safely today. The failure writes the code, the builder receives the bill. All right, moving away here. That infrastructure bill pays for what all that computing can deliver, but our next story moves from a grid spanning several states to the thin layer of tissue at the back of the eye. Inherited retinal diseases cause progressive vision loss. More than 280 genes have been linked to them, and that creates a hard diagnostic problem. Many conditions can look similar through an eye exam, while the treatments often depend on the specific gene that is involved. Patients may spend years moving through specialist referrals and genetic sequencing before finally receiving a confirmed genotype. Retina for IRD offers a faster path now. That system appeared in Nature Medicine on July 24th, and it reads retinal images and predicts which of 17 different genotype categories a patient's condition most likely belongs to. Its foundation is a vision transformer pre-trained with RetFound, which is a model built to learn patterns in retinal images. So a vision transformer processes an image in pieces, much like a language model, for example, processes a sentence in tokens. It learns how those pieces relate across the whole retina. Researchers trained Retina 4 IRD on images from 1,843 patients across China, South Korea, and Poland, and on its internal test, the corrective genotype category appeared among the model's top 5 suggestions just over 90% of the time. On a separate external group, it reached nearly 86%. So those results are really strong. The more important evidence, though, came from testing the system alongside doctors in a randomized controlled trial. Most medical AI studies look backwards. Researchers collect old cases with known answers and ask whether a model can recover those answers. Now, that can prove a system recognizes useful patterns, but it tells us less about how the system changes real clinical decisions. This trial compared specialists working with Retina 4 IRD against specialists working alone. Among 295 analyzed participants, doctors using the system placed the correct genotype category in their top 5 choices nearly 89% of the time. Doctors working without it reached about 67%. So that difference was statistically significant, with a probability below 1 in 1,000 that random chance alone explained that gap. The doctors also chose better next steps too. The study measured whether their plans for follow-up and patient management fit the case. That score rose from 28.5 to 37.7 when the clinicians had the model's help. That is the partnership result. Now, the retinal specialist will still examine the patient to consider the history, order the genetic test, and decide what happens next. The AI sees patterns in the image that a human eye may not be able to map to a particular genotype. That is the partnership. It turns the diagnostic search across more than 280 possible genes into a short-ranked list of genotype categories, and that can change where advanced diagnostic judgment lives. Today, much of that expertise remains concentrated in academic hospitals and specialist centers. An open system that works with standard retinal imaging could carry part of that judgment to regional clinics. The researchers published the code openly, and that gives other teams a chance to test it, adapt it, and find where it fails. Openness like that also builds trust. A clinic shouldn't have to rely entirely on some commercial claim when researchers can examine the system itself and reproduce the work. The commercial incentives, of course, still deserve a clear reading, though. The senior author co-founded a company working in this area. The corresponding author consults for several pharmaceutical firms. Now, those conflicts don't erase the trial, but they do give everyone a reason to demand independent validation and close scrutiny of any later product claims. So the trial does demonstrate a capability. It does not establish a finished clinical service. Regulatory clearance still lies ahead. Hospitals would have to connect the model to their imaging systems, and then researchers would need to validate it prospectively in the populations where it will be used. So no, a patient can't walk into any regional clinic and receive this analysis as ordinary care yet. But the direction is striking, especially considering how many of these different breakthroughs that we have been covering. An inherited disease begins with a change in DNA. That change leaves the patterns in the retina, and then an AI can now read those patterns and give a specialist a far better place to start looking. A search that once wandered through years of referrals may finally begin with a single image. All right, shifting over here. Once clinicians identify the gene, medicine faces the next problem, changing it safely. And that brings us to the treatment side of this same pipeline. Gene editors use Cas proteins as molecular scissors. A guide points the protein toward a chosen DNA sequence, and the editor makes a change at that specific site. Sometimes the editor also acts somewhere else. Those off-target edits are one of the central safety barriers in gene editing therapy. A treatment that is intended to correct one gene can accidentally cut another sequence that looks similar enough to confuse the editor. So researchers have now used AlphaFold to attack that specific problem. AlphaFold became famous, you'll remember, for predicting a protein's three-dimensional shape from its amino acid sequence, and that helped scientists see structures that previously required years of very difficult laboratory work. In a Nature paper published in July 22nd and covered by Ars Technica just 2 days later, researcher gave AlphaFold a different job. They used it to identify the specific regions of gene editing proteins associated with these stray cuts, and then they redesigned those regions to lower the error rate while preserving the intended edit. This is a deeper role than just predicting a finished shape. The model helped researchers reason about which part of the molecular machine causes unwanted behavior and how that part might be rebuilt. Human researchers can test a handful of changes suggested by experience, but a model can explore a much wider space of possible protein designs and surface combinations that a person may never even think to try. And the choice of target counts, too. Earlier this month, researchers used AI to build new gene editors from scratch. This team worked on editors already moving through the therapeutic pipelines. Clinical programs have spent years learning how these existing editors behave. They have built delivery methods and safety tests around them. Throwing out the editor would also throw out part of that work. Improving the existing protein asks for something harder: preserve the action researchers need while removing the molecular habits that they don't. That is what this study moved toward. Now, the work remains in structural and biochemical assays. Patients can't receive an AlphaFold redesigned editor as an approved therapy right now. Researchers still have to test how the redesigned proteins behave in cells, animals, and eventually human trials, and then they have to watch for immune reactions and delivery problems and off-target effects that the existing assays may miss. And the need for that process became painfully clear just 2 days ago when we covered the concealed death in the Shanghai-based editing trial. A 6-year-old girl died 7 days after an infusion following a severe immune reaction, and the research team's Nature paper omitted both her death and her family's roughly $800,000 payment. Now, that case involved delivery and oversight rather than the specific off-target problem that AlphaFold addressed. It still belongs, though, beside this progress. The chemistry can improve quickly, while disclosure, trial design, and institutional accountability lag behind. A safer editor only reaches its promise through honest testing. Every bad outcome has to enter the record. Every risk has to survive outside scrutiny. And that honest counterweight makes the AlphaFold result more valuable. Gene editing needs improvements that lower risks inside the molecule. It also needs systems that surface risks around the patient. AI can help with the first, but human institutions remain responsible for the second. Together, the retinal trial and this protein design study show two ends of a medical path moving at once. One system looks at an image and narrows the gene behind the disease. Another helps reshape the protein that may one day correct it. Diagnosis and treatment have long advanced on separate timelines, but AI is beginning to pull both forward in the same research cycle. All right, we have followed AI from electrical infrastructure into diagnosis and molecular design, and the final story brings it into physical action. FLUX 3, the multimodal foundation model from Black Forest Labs, is now running robots at Audi's production lab. Now, we covered the model's launch just a couple of days ago on July 24th. This new development is the production deployment and what its training reveals. FLUX 3 spends more than 95% of its training compute predicting video. It watches how one frame becomes the next. An object falls, a hand closes around a cable, a flexible seal bends when pressed against another part. To predict those changes well, the model has to learn something about cause and effect. A video model can't produce a convincing next frame if it treats the world as a pile of unrelated pixels. It needs a working sense of motion and contact and shape and what objects tend to do after something acts on them. That makes the model a world model. You may have heard us talking about these before. Black Forest Labs built a companion action system called FLUX Mimic, and it reads robot actions from FLUX 3's learned picture of how things move. The same foundation that generates images, video, and audio can now guide a machine through a physical task. At Audi's production lab, the robots handle kitting, inserting electronic control units, assembling components, and manipulating flexible materials. Now, that last category, the flexible materials, is especially important because traditional factory robots thrive when every object arrives in the same place and holds the exact same shape. Their movements can be measured and programmed and repeated endlessly. A metal panel behaves predictively then. A cable that is flexible does not. Seals bend, flexible parts twist. A cable changes position when the robot touches it. The machine has to see the change, predict what comes next, and adjust the movement accordingly. Christoph Schneider of Audi's production lab said this kind of soft body manipulation was effectively impossible with the rigid, pre-programmed systems used before. FLUX Mimic reacts in 101 milliseconds. Mimic Robotics says that it has reached up to 10 times the sample efficiency of earlier vision language action system. Now, sample efficiency tells us how many demonstrations a robot needs before it can perform a task. 10 times the efficiency means that engineers can teach it from roughly 1/10 as many examples, and that changes the economics of factory automation. A robot that needs an enormous library of demonstrations may only make sense for a task repeated millions of times. A robot that learns from a much smaller set can move between tasks more easily. Engineers can retrain it when the product changes, the component moves, or a new assembly step arrives. The model also had to reconcile its two different jobs. When researchers first added action prediction, the model's video quality ratings fell by as much as 10%. After 3,500 training steps, the quality then recovered fully. So the model learned to generate the world and act within it without sacrificing either competence. And for most of computing history, those jobs lived in separate systems. One program would render or predict what the world would look like, and another controlled motors using rules created by engineers between the two. FLUX 3 weakens that division. If a model becomes very good at predicting the next frame of reality, then it already contains much of the knowledge that a robot needs to decide what motion should produce that frame. So the route from pixels to actions becomes much shorter. And that is a genuine breakthrough. It also arrives, though, with real tension for the people working on factory floors. Of course, a worker who sees a robot handle the flexible pieces that previously required human dexterity may reasonably hear a threat to their wage and bargaining power. Now, that fear comes from how companies choose to deploy the capability and distribute its gains. It does not come from some flaw in the ability itself. A robot that can manipulate soft materials could take dangerous, repetitive, or physically punishing work away from people. It could also become a way, though, to remove workers while keeping all the savings above the factory floor. The technology doesn't decide which arrangement follows. Ownership, labor power, and access do. Now, that distinction is really important because the underlying capability will travel far beyond just one production line. It's going to explode outward as robotics capability improves. The same kind of physical understanding can help robots handle hospital supplies, sort recycling, work with agricultural products, or operate in other places that might be unsafe for humans entirely. Now, each task becomes easier to teach because the model has already learned a general picture of how the physical world changes. Now let's take a step back and look at the striking part, which is where that knowledge originally came from. Black Forest Labs began with a media model. More than 95% of its compute went into watching and predicting video. Inside that job, it learned enough physics for a companion model to guide a robot through soft, shifting materials at Audi. So the machine that learned to imagine the next frame can now help make that frame happen. All right, let's bring it to a close for today. A single downed line exposed the bill for this transition. More than 3 gigawatts of computing load disappeared in about 30 seconds. The grid reacted across several states because AI campuses have become large enough to shape the electrical system around them. That bill is physical. It includes new generation, transmission, storage, ride-through controls, and the work of protecting nearby communities. Companies building the load have tried several different ways to leave part of that bill elsewhere. Virginia regulators downplayed residents' concerns. The EPA is moving to narrow public notice around backup generators. Some operators have pitched private gas turbines as an escape from the grid, only to fall short of their own promised capacity. Physics keeps returning the cost to the shared system. Binding rules are starting to return it to the builder. And then we've also seen the dividend. Retina 4 IRD helped specialists find the right genetic category from a retinal image, lifting their accuracy by more than 20 percentage points in a randomized trial. AlphaFold helped researchers locate the parts of gene editors responsible for stray cuts and redesign those regions. FLUX 3 learned enough about physical cause and effect from video to guide robots through flexible factory parts that rigid automation could not handle. Those capabilities don't excuse the infrastructure cost, but they show what the infrastructure can make possible when the gains reach beyond just the top of the companies financing it. The medical work still needs regulatory review, independent validation, and honest clinical oversight. The factory deployment still raises hard questions about who benefits when machines learn work that people perform today. Those tensions belong in this account, but so does the scale of what is opening here. A retinal image can narrow a genetic search that once took years. A protein model can help refine the molecular scissors meant to treat a disease. A media model can turn its learned physics into physical action. The grid underneath all of it has to grow into the same level of competence. It needs to sense, absorb, and balance a new kind of demand. Data centers need to stay connected through ordinary disturbances. Campuses need enough storage to protect both their computers and their neighbors. The answer is not no more AI or none of this anymore. Absolutely not. The promise is immense, and anyone still claiming that AI has no actual capability or actual impact on a better future is absolutely fooling themselves. Now, the July 22nd failure points past today's limits. It hands engineers the next set of requirements. That is the hopeful payoff here. The grid can hold far more intelligence than it carries today. It will do so because each failure makes hidden assumptions visible, turns voluntary promises into engineering rules, and pushes the true cost toward the projects creating it. 2 nuclear reactors worth of demand behaved like a light switch. Now, that switch has been seen, and the standards can be built around it, and the next grid can become strong enough to carry the dividend and continue the benefits of AI for the future. We'll see you tomorrow.